Welcome back. In this video, we're going to go over section 4.4, which is about systems of equations that have three variables in them. So far we've seen systems of equations that had two equations with two variables. We looked at substitution and elimination as methods for solving, and we looked at a bunch of story problems. In this section, we are looking at what happens if you have a third variable and a third equation, and all three equations have three variables in them. So that's this. Okay, so for this, a linear equation in three variables looks like ax plus by plus cz equals d, where the a, b, and c are just numbers, and the variables are x, y, and z. So that's a linear equation in three variables. And again, when we say it looks like, that means that we could also rearrange the terms and apply like some algebraic manipulations to the equation, and it still would be considered linear. The key thing, though, is that there's no x squareds or, square root of y or anything crazy happening like that, okay? For one of these, the graph is a plane. We talked in earlier sections about the two-dimensional case, about how the graph of a line, you could consider a system of equations solution to be the point of intersection, if any, on those two lines. The geometric interpretation for this one we'll get into here in a minute, but basically the graph of one of these is going to be a plane in three dimensions. I don't mean like an airplane. I mean like a sheet of paper or the floor in your room, a plane. Okay, a solution to one of these is going to be an ordered triple of numbers instead of an ordered pair. It's going to be an ordered triple of x, y, and z. So a system of linear inequalities, that should be equations. A system of linear equations in three variables looks like this. X, for example, x minus y plus z is 2, 2x minus y minus z is negative 6, 2x plus 2y plus z is negative 3. So three equations with three variables in there. And as I said, there is a geometric interpretation to this that we're not going to get into too deeply just for a second. In three dimensions, if we all know what the xy plane looks like, a three-dimensional coordinate system would have a x number line that points straight out towards you, a y number line that moves from left to right, and a z number line that moves up and down. So any point in three dimensions can be described by a triplet of numbers. How far toward you, how far from left to right, and how far up and down. And then there's plenty of advanced math classes that go into a great deal involving this, but for our purposes, suffice it to say that there is a geometric background for what we're about to do. Each of these linear equations in three variables, its graph is going to be a plane, like a sheet of paper or the floor of your room. And so if we're going to consider a solution to such a system, we want to think about what that might be like. A solution, if there's a unique solution to this, is going to be the point of intersection of three planes. For example, what's shown here is the point P in this graphic. Another example would be if you picture the room that you're sitting in right now. This is difficult because I don't know where you are, but if you're in a room, let's say you're in your bedroom, if you consider a plane described by the floor, by the left wall, and the wall in front of you, there's going to be one point in common to all three of those planes, and that would be the solution to that system of linear equations in three variables. What other situations are possible? We could have the three planes intersecting in a line. That would give us infinitely many solutions. We could also have no solution. Here in this picture, there's no one point that is in common to all three planes. Here in this picture, there's points in common to 2 out of 3 of the planes, but not all 3. And here there's no points in common to all 3 planes. We're not going to get into the whole dependent versus independent, consistent, inconsistent thing. We'll just say, okay, well, is there a solution? If there's a solution, we'll be able to find it, and we'll have its coordinates x, y, z. And if not, there may be infinitely many solutions, or there may be no solution. We'll focus on the situation where there is one solution and how you go about finding it. But kind of keep in the back of your mind that there's more. if you want to find out about it, and that'll be in higher math classes. Okay. So what we want to do as a first example is just decide if a couple of triplets would make up solutions to a system of equations. So let's try first with the point 1, negative 3, 2 in this system. So if it's going to be a solution, it has to satisfy all three equations. And so let's check. So we'll have 3 times 1 plus negative 3 plus 2. Let's see what that's equal to. So 3 plus negative 3 is 0, plus 2. Okay. All right. So sorry about that. Zoom crashed once again. Let's try the second equation. We have x, which is 1, plus 2y's plus z, and that's 2. You need to see what that's equal to. So 1 plus negative 6 is negative 5. Negative 5 plus 2 is negative 3. So that worked out. And then the last one, 3 times 1 plus negative 3 plus 2 times 2. So 3 times 1 is 3, plus negative 3 is 0. 2 times 2 is 4, and that equals 4. So yes, that worked out. So this one, it satisfies all three of the equations, so that would be a solution to the system. Okay, so then let's check on the next one. So putting the point into the first equation, 3 times 4 plus negative 1 plus negative 5. That's 12. Minus 1 is 11. Minus 5 is going to be 6. And that's not equal to 2. So this point didn't even fit the first equation. We don't have to check the other two. So it's enough to say that no, this one is not a solution. In order for a triplet of numbers to fit or be a solution of a system of equations, it has to satisfy all three of those equations. Okay, fortunately, there's kind of a set procedure you can follow to help solve one of these systems of equations. So let's go through the steps to follow. Let's organize things a bit. All right, so the steps to follow go like this. Use any two equations you like to eliminate a variable. Then use a different pair of equations to eliminate the same variable. So those are important. So the first step, use any two equations you want to eliminate whatever variable you want. Total freedom in that first step. Once you've committed, you need to eliminate the same variable in step 2 by using a different pair of equations. This will give you a 2x2 system that you can solve. And then once you've found that solution to that 2x2 system, you can back substitute to get the solution to the 3-variable system as a whole. All right, so the best way to see how this goes is by doing it. And so let's try. For our purposes, discussion purposes, I'm going to go ahead and number the equations that we're working with. That way I can refer to them. This also helps me if I get stuck and I have to go back and I want to try to figure out what it was that I did. Okay, so taking a look, we do get ultimate choice in the very beginning. We could use the second and third equations to eliminate z's. That would also eliminate x's, it looks like. And we could also, right, so we're back. So again, you can eliminate any variable you want using any equations you want. I think it's going to be easiest to eliminate variables using equations 2 and 3. So let me write a recipe for a fourth equation. So we're going to get an equation 4, and we're going to get that by adding together equations 2 and equations 3. Circled numbers are equation numbers, okay? So this is just a reminder to myself that I'm adding together equations 2 and 3. This is going to give me a new equation 4. Okay, so let's try. So negative 2x plus 2x is no x's. Negative 2y plus 3y is a single y. Negative z plus z is no z's. And then 2 plus 1 gives 3. Okay, so this one we got lucky at the very beginning. We found out right away that y was 3. And so we can just go ahead and rewrite our system, replacing the y with a 3. So let's do that. So we will have 4x plus 3 plus z is negative 1. We'll have negative 2x minus 6 plus z is 2. And then 2x plus 9 minus z is equal to 1. Okay, so this is our system of equations with y replaced by its value of 3. So then let's collect the constants all on one side for this. So we'll have 4x plus z, and then that will equal negative 4. And then we'll have negative 2x plus z, and that will equal 8. And then we'll have 2x minus z, and then that will equal negative 8. All right, so now you'll notice on this that the second and third equations are just opposites of each other. If we were to add these two together, we would get an equation like 0 equals 0, which is not helpful. And we'll talk about that more in a later example. So it turns out that equations 2 and 3 are equivalent to one another, so they don't provide us any additional information. Instead, let's take and use equations these two equations, which let me give these numbers. Let's call these ones 5 and 6, just so I can refer to them. I'm going to get a new equation 7, and we'll get that by taking equation 5 plus 2 equation 6's. So we can multiply an equation by a number and add it to another equation. So that's what we are doing here. So we're going to take equation 5, and we'll add it to 2 of equation 6. So very carefully. Okay, so we have 4x plus negative 4x, which will be 0x. And then we'll have z plus 2z is 3z. And then we'll have equation 5, that's the negative 4. And 2 8s will make 16. 16 minus 4 will be 12. So we have 3z is 12, and from there it follows that z is 4. Okay, so if you find this rough going, by the way, it's totally natural, and it will get a little bit better with practice. So now we have y, we have z. We can back substitute to find the value for x. We can do that using any equation that you want. I think it'll be kind of convenient to use maybe that one, the yellow highlighted one. We'll use that. Okay, so then we have 4x, which we don't know what that is, plus z, and that's 4, and that will equal negative 4. So a nice little equation to solve. We'll have 4x is negative 8, so that x is negative 2. Okay, so we finally got all three variables, so we're going to report our value as a triplet. The x comes first, that's negative 2. Then we'll have a y of 3, and then a z of 4. Okay, all right, so that's how that goes. We're definitely going to do more examples, but that is how our first example plays out. Okay, let's try that again. All right, so for this one, we have the equation or system of equations that's shown. As before, I'm going to number the equations so that we have something we can refer to. All right, so once again, we have to decide on a variable that we'd like to eliminate. I would go with whatever seems easiest. So taking a look, I think probably it's going to be nicest to eliminate y's, because in equations 1 and 3, their coefficients are opposite of each other. All of the others, x's or z's, we would need to multiply one or more equations by something in order to make it happen. So let's not do that. We're going to get an equation 4. And that equation will be equation 1 plus equation 3. Okay, so we're going to add equation 1 and equation 3. We'll get equation 4. So 3x plus 4x is 7x. Y plus minus y is no y's. That's why we did it. And then minus z minus 3z is negative 4z's. And then 2 plus 0 is 2. Okay, this gives us an equation with x's and z's in it. Okay, so this is the result of step 1. We used 2 equations to eliminate one variable. Now we need to use a different pair of equations to eliminate the same variable. So we eliminated y before, so we're committed to eliminating y's. I've used equations 1 and 3 before, so now we have to use 2 because we haven't used 2 yet. We have to involve it. So we're going to get a new equation 5, and that has got a negative 3y in it. So I want to use it along with one of the other equations to eliminate y's. So negative 3y, if I use the top equation, at least that's opposite in sign. If I just added those two together, the y's would not be eliminated. It would be helpful if this were 3y instead, but it isn't. But what we can do is multiply equation 1 by 3 and add it to equation 2. If I multiply equation 1 by 3, that's going to create that situation where the y's have opposite coefficients. Okay, so 3 times equation 1. So 3 times 3x is 9x. 9x plus 2x is going to be 11x. So I'm going to stick with my colors. So we'll have 11x. 3 times 3x is 9x. Plus 2x is 11x. 3 times y is 3y. Plus negative 3y is no y's. That's why we're doing it. 3 times minus z is minus 3z. Minus 3z minus another 2z is negative 5z. Okay, 3 times 2 is 6. Plus 1, 7. Okay, that's not a plus, that's an equal. All right, so this gives us, you'll notice, a second xz equation. So we'll have 7x minus 4z is equal to 2. We'll have 11x minus 5z is equal to 7. All right, so we've eliminated y's. This gives us an equation just in x's and z's that we should be able to solve. So let's work on that. All right, so let's see, what should we do to eliminate a variable here? If we work with z's, the numbers are smaller. We're multiplying by 5 and 4. If we were to work with x's, we'd be multiplying by 11s and 7s. So I'm going to go with z's just because the numbers are smaller. They are both, either way, the coefficients are not opposites of each other, so that's not a help. So we're going to multiply the first equation by 5. So actually, let's make that negative 5. So if we make that negative 5, we'll have negative 35x plus 20z, and that's equal to negative 10. And then our second equation, we're going to multiply by 4. Okay, then we will have 44x, and we'll have minus 20 z's, and then that will be 28. Okay, now we can add together the pieces. Negative 35 plus 44 will be negative 9. So we'll have negative 9x. There are no z's. And then 28 minus 10 is going to be 18. So negative 9x is 18. That will make x be negative 2. Okay, once we found the value for one variable, we'll start working our way back. Again, it doesn't make a difference what equation we back substitute into, as long as we have the all but one value for, or one value for all but one of the variables. So I'm going to plug it back into this equation just because it's close. So 11x, that's 11 times negative 2, minus 5z is 7. So negative 22 minus 5z is 7. Negative 5z, we're going to add 22 to both sides. That'll be 29. So z looks like negative 29 fifths. Okay, I'm going to double check my work here because often the problems in math books work out nice and clean. with no fractions or minimal fractions. And the fact that this is 29/5 makes me worry that it's wrong. So I'm going to go back and double check. All right, so taking a look back over my work, I found a mistake, which let's fix that. So here, when I had negative 35x plus 44x, somehow I had gotten negative 9x. That should be positive 9, right? And so that'll be positive 9x. And so 9x is 18. That will make x positive 2, not negative 2. So carrying the change forward, if x is 2 here, we'll have 11 times 2, which is positive 22. And then we'll have 7 minus 22 on the right side here. And that'll be negative 15. If negative 5z is negative 15, that'll make z be 3. So that was an honest mistake. So sorry about that. But I did want to point out that often with these system of equations problems, especially the 3x3 ones, because of the amount of work that's involved, in fact, this is a math class, they're often rigged so that the numbers come out relatively clean. If you find yourself running across fractions, not relatively friendly fractions like a half, a third, or a sixth or something. Here I'd had, I forgot what I had already, 29/5. If you start getting some unusual fractions, then go back and double check your work because it could be that you made a mistake like I did. All right, so we got z, we got x. Now all we have to do is go back and get y, and then we're all finished with this. So it doesn't matter what equation we use. So I'm going to get this first one, I think. So we'll have 3x, that's 3 times 2. And then y we don't have yet. And then z was 3. And this will be 2. All right, so we'll use that information to help us find out y. So we'll have 6 plus y minus 3 is 2. 6 minus 3 is 3. So we have y plus 3 is 2. That makes y be negative 1. All right, so finally, after all that, we have the values for all 3 variables. Our x worked out to be 2. After the correction, our y worked out to be negative 1, and our z worked out to be 3. Okay, so that takes us to the end of this problem and the end of this first part of this video. We'll have more examples to come in the next part. In the meantime, let me know if you have any questions. Have a great day.